Hi, everybody. Today I'm going to talk to you guys about momentum. Now, momentum is one of those concepts that has multiple different meanings depending on the context in which you use it. In everyday life, oftentimes, momentum is used in a situation in which there's an emotional context. So, like a football game, you may feel like everything is going your way, and so you have all of the momentum. That is somewhat like what the physics concept is. The physics concept is also about things going a certain way, but it's also about how things interact when they collide. And so we're going to talk about both of those things. So whenever you try to apply Newton's third law, it's helpful to think about it in terms of momentum. So momentum is defined by your textbook as inertia in motion. Now you might remember that inertia was this concept that's related to mass that says an object in motion will tend to stay in motion, and an object at rest will tend to stay at rest until acted upon by an outside force. That's Newton's first law, or the law of inertia. This idea of inertia is that objects resist a change in their motion. Now, it's often confused with this idea of momentum because they're very closely related. So if an object has its inertia because it has mass and is also in motion, we can talk about it in terms of its momentum. So it has both its inertia because it has mass and motion as well. And so as you know, if I were going to relate these two concepts, inertia and motion, to our two most important physics concepts that we've learned so far, they would be inertia is mass, right here, and motion would be velocity. And so momentum is going to be related to both of those two things. So what is momentum actually? Well, we find out that momentum, which is indicated with a lowercase p, is equal to the mass of the object multiplied by its velocity. That's it. That's all there is to it. Momentum is equal to the mass times the velocity. Now, here's my question. What kind of quantity is mass? Is it a scalar or is it a vector? Hopefully you're thinking it's a scalar for sure because mass doesn't have direction, but velocity does. And so I'm going to indicate that this is actually a vector by putting a little arrow above it to help to remind you that it's a vector. So if I have a scalar quantity times a vector quantity, do you think this momentum is going to be an object or a quantity that needs a direction or not? And the answer to that is really what you want to think about when you go back to the emotional context. So the emotional context, remember, I said in a football game, you may feel like everything is going your way. So it's going in your direction. And so you can think that momentum is, or does have to have, a direction. So it's a vector. There we go. So momentum is a vector. It does depend on which direction you're going. Now you can see this might be important if you're talking about how if two cars are coming at each other and they collide, that's going to be a very different situation than if two cars are going in the same direction and they collide. So the direction is going to be very important when we talk about momentum. So we are always worried about our units in physics, and so I wanted to make sure to let you know that the units are kind of strange for momentum. That's okay. Just keep that in mind. It's nice when you have a unit that kind of summarizes things, like the Newton actually means kilograms times meters per second squared. So that's cool to have that, but unfortunately momentum doesn't have that. So we have to just take the units that we have. So momentum is equal to the mass. Mass is kilograms. And it's multiplied by the velocity. So velocity is meters per second. So the units for momentum are just kilograms times meters per second. It looks like this. Nothing fancy about it. Again, kilograms times meters per second. Okay, so in the last video, we talked about how Newton's second law isn't really in its best form for us as humans. So F equals ma is nice to remember, but it's not great for a feeling of physics. So what we did in the last video was we took F equals ma and we combined it with A equals delta V over delta T which is the definition of an acceleration, the change in velocity over the change in time, and we combine them. And so if you combine them, you sub in where a is, you sub in this delta v over delta t, and then you solve for this formula right here. And this is the important one. It's called the impulse momentum theorem, and it's called that because this stuff on this side is the impulse, which is what we talked about in the last video. So impulse is F times delta t. Now remember that the units that we used for impulse were newtons times seconds, and we can summarize that with a capital J if we want. Okay. On the other side, though, we kind of let it go we haven't really talked about what's going on the other side. So if you think about it, we've used this formula, but we didn't really define what that is. And so let's talk about what that really is over there. Well, now you know that momentum is actually the mass times the velocity. So here's my question. If momentum is mass times velocity, what do you think mass times the change in velocity is? Hopefully you're thinking it's the change in the momentum, and that's exactly what we find. So we have the change in momentum here. How much the momentum changes when two objects interact. Change in momentum. There we go. Now, we found just a minute ago that the units for that are a little strange. They're kilograms times meters per second. And as you might imagine, when we want to symbolize change, we use a delta. And when we want to symbolize momentum, we use a little p. So it's actually symbolized with this delta p right there. That's hopefully you can see that. There we go. So delta p. So J equals delta p is the impulse momentum theorem. This theorem says that the force times the time equals the mass times the change in velocity. And I think it's a super helpful thing to know if you're trying to use Newton's second law to do anything. And especially if you're trying to apply Newton's third law to a situation in which you have a collision. And that's what we're going to do basically for the next 2 weeks or so. Okay, so let's give an example here. So I have a rocket car, and the rocket car starts off with an initial velocity of 0. And I know for a fact that the rocket that's been mounted on this car applies an average net force to the car of, let's say, 1,000 newtons. Okay, so the average net force is going to be 1,000 newtons. Let's also say that the mass of the rocket car is 500 kilograms. As you can tell, I'm not worried about sig figs here. I'm just trying to make a point. So my question is, what's the final velocity if I apply it over a certain period of time? Now, let's imagine that the time is actually 10 seconds. So let's see how fast you're going after you fire that rocket with an average net force of 1,000 newtons for 10 seconds. So I'm going to go ahead and put down that the delta t is 10 seconds there. There we go. Okay, so we have a formula for this, and that's the impulse momentum theorem. And so really what I want to try to find is what's the final momentum of the car, what's the final velocity of the car. Either way will get me to the right answer. So I know that it starts at 0, and I know that I want to know what it ends at. So I can apply that simple impulse momentum formula to be able to figure that out. So the impulse momentum formula says F delta t equals m delta v. Now, delta v is actually, if you think about it, a simple way of saying the second velocity minus the first velocity. Now I'm going to write that like that because I really want to know what the second velocity is. So I do know the force, the average net force is 1,000 newtons. I do know the time is 10 seconds, and I do know the mass is 500 kilograms. And so I can use that to figure out what the final velocity is, especially knowing that I simplified things by making the initial velocity 0. So that initial velocity is going to go away, and I'm going to bring the mass over to the other side. So I end up with this, F delta T divided by M gives me V sub 2. So now my formula is solved for the correct variable, and I can go ahead and plug in. And so I plug in 1,000 newtons times 10 seconds divided by 500 kilograms, and that should give me what my answer is. So 10,000 on the top divided by 500 on the bottom should give me 20, right? So what's my final velocity? Is 20 meters per second. Not very cool for a rocket car, I have to admit, but I chose numbers that would make the math a lot easier for me so I could do it in my head. So it starts at 0 meters per second and it ends at 20 meters per second. So it has a final velocity of that. So its final momentum, P, and you can say P2 since you want the final momentum, is equal to its mass times its final velocity. The mass is 500 kilograms and the final velocity is 20 meters per second. So we should have 10,000 kilograms times meters per second. And that's the momentum. Now, remember that momentum is a vector and velocity is a vector. And so in this case, I could say, if it's to the right, I could say positive right there, just to indicate that it's to the right. I could also, if I wanted to, put down a little R for right, something along those lines, just so you know what the direction is. Why is that important? Because let's say, heaven forbid, that the rocket car hits a wall or hits another car that is moving in its own way, we are going to have to try to figure out what happens to the car as a result. And that's going to be based off of the momentum that it has and the momentum of the thing that it hits, which is what we're going to talk about in the next video when we talk about collisions.